In this video, we'll discuss how to investigate regression diagnostics using R. Now, in most of the R videos, I haven't been giving you the code, expecting you to type it as you follow along to get practice in typing all this, entering it yourself, dealing with some of the errors that R spits out, troubleshooting all that. All of this is so important, and this is what we would normally do in a regular class. That said, at the beginning of this video, we're going to discuss making example data sets, and it's really important that you get all of this right to be able to follow along with the rest of this lecture. Because of that, I've gone ahead and posted the making example data sets code in a small R file attached to this video on Blackboard. So make sure you get that downloaded, and that way you can copy and paste all this and you don't have to write this. I didn't give you the rest of the code so that you can practice typing that out as you're following along, but I did give you this one again because it's very important to make sure you get this right. Okay, so first I'm going to be generating some random data sets with known features or details such that we can identify, as we're looking at different tests of assumptions, which variables will have fine assumption tests and which ones will break. And then we can look at how the statistical tests of assumptions function within all this, as well as the plots. All right, so when I'm making random data, it's important that I first use the set seed command. What this will do is this will line up your computer with my computer such that when we make random data, our computers make the same random data. Now, I tend to use some date, so I tend to use whatever date I write the code on. You can, or record the video on, you can do a different date. Put your birthday, you can put, I don't know, any random day, you can just put a random number in there, but it's important that you stick a number or a constant in there and not like R norm or something that would generate a random number. What you want to do is stick a constant into the set seed, and that impacts the rest of the random number generation you'll have. Now I'm going to be using 100 values, and you can do this activity with a different number of data points. If you wanted to do it with 10 and see how things change, that's fine, or you could do it with 30, or you could do it with 1,000. All of the numbers of data points are definitely going to impact how each of the features of what we do from now on in this video behave. So you can play around with that to see how each of the different features function. Now what I'm going to do is I'm going to create just a whole bunch of x values between 4.94 and 5.56, and these x values will be the 40-yard dash time for a bunch of people in an NFL combine. I'm going to use the beta 0. This is the intercept, so I know the population intercept. I'm making it here. And negative 1.466, this is the population slope. And I'm going to use these to create my model of y. So y is beta 0 plus beta 1 times x. But don't forget that we have this plus epsilon, or plus random error. So I'm going to create normal random errors. I'm going to create n of them. They're going to have a mean of 0 and a standard deviation that's constant. That constant's going to be 0.15. So if my MSE were perfectly accurate, it would be 0.15. It's not going to be, but that's okay. So now I have my y values that are centered around this beta 0 plus beta 1 times x. That's the y hat that we'll eventually get. And then they have some random error associated with them. Okay, so this is the data that is going to meet the assumptions. If I look at the relationship between x and y, this is the first relationship that we'll look at down below. That relationship should be just fine on the checks of assumptions. Now here I'm going to generate several different data sets that don't meet specific assumptions. So I'm going to make a not linear data set. This will be a quadratic data set. So I'm just going to change the beta 0, beta 1, and beta 2 to be different numbers, and my y for this second example, I'll call it y2, is going to be a quadratic. It's going to be one value plus beta 1 times x plus beta 2 times x squared. So you can see that this is going to be a quadratic equation, and it's not going to be linear. And then I will add my errors here, and this should be epsilon. So I guess you should fix that in your code too, because if I have it wrong in mine, you probably have it wrong in yours. Okay, and then we have, let's see, So this example is going to be not normal. So now my errors are going to change. My errors are going to be a uniform distribution instead of being a random normal distribution. So again, we assume errors are normally distributed. They were up here, but now they're going to be uniformly distributed. And so I'll do that, and Y3 is going to be the same exact regression model, except now instead of the errors being the normally distributed epsilon, it's going to be epsilon 3, which are the uniformly distributed errors. And we'll just see what happens if you move from a random normal distribution of errors to a uniform distribution of errors. We'll see if anybody even notices. All right. So for the fourth one, we'll do no homogeneity of variance. So we'll take this epsilon, it'll be normally distributed, but instead of having a constant x, a constant value for the standard deviation, now we'll have the standard deviation be a function of x. So the standard deviation is going to change depending on what the value of x is, and we'll see how that impacts our y values. And then in this final example, we're going to have multiple issues. We're going to use a quadratic, and we're going to have the homogeneity of variance change. So this is one where we're going to have multiple violations at the same time, and we'll see how that functions. So again, all that's that pre-typed code if you grab that, except for this epsilon piece where you have to type that into the quadratic. Now we can move on to actually checking our assumptions. Now the below are broken down by assumption. So typically, as we mentioned in the lecture, you can have it broken down by assumption, or you can have it broken down by the different plots and then look at all the assumptions together. Typically, we just plot the different plots and look at all the assumptions together. But for this first one, we'll break it down by the assumption, and we'll look at linearity, then independence, and so on. So the first thing I do is I fit the model. Now I don't even look at what the parameter estimates are, or I don't look at the significance tests, because I don't care until I've checked the assumptions. Remember, we check the assumptions first before we interpret. So I'm going to go on and create my residuals, and I'm going to create my predicted values. You can do that either by doing predict mod or fitted mod, but both of these will create predicted values, or y-hats. It's a shortcut. In R. Now for linearity, we can look at a scatter plot. Don't forget that in this course, we really like your plots to be nice and nicely labeled. So, put a nice title on it, put a nice x-axis and a nice y-axis on it. And then we have AB line, so this is just going to add the best fit line. Notice that I'm looking for linearity. So does the relationship between x and y appear linear? And in this case, yeah, it does. There doesn't appear to be any curves or anything weird going on. It appears to be roughly linear. That looks fine. The next one we can do is the residual plot. So in this residual plot, we have the residuals, we have the predicted y values, and we're looking for any patterns or curves or anything like that. We don't really see anything that would catch our attention. Maybe this point's a little high, but even that doesn't look too bad. It looks pretty reasonable, a random scattering of dots, which is what we would expect to see in a good-looking residual plot. This looks perfect. Now for independence, again, independence comes from the methodology. So as I know that this data was randomly generated because I just randomly generated it, I know that this data were independent. However, what we could do if we had a data set that was in time order is we could plot the y values in time order in that sequence plot that we discussed. Now I'm doing this to demonstrate, but again, you should not do this unless you know for certain that your data were given in time or order. So in this case, if we wanted to plot y in order, then we would just use the command plot y. And we can do this because the default x values are the order of the data, 0, 1, 2, 3, 4, 5, 6, etc. So the default x values are going to be the order of the data. So if I don't enter an x value, then the y's will be arranged in terms of the order in which they're presented in the data set. Now for normality, I can do a histogram here. So I'll do a histogram of these residuals. So this is my histogram. Kind of looks roughly normal. We can overlay a line here. So I'll make a sequence going from a little bit below the minimum to a little bit above the minimum, above the maximum of the residuals, and I'll do this using the normal distribution with a mean of the errors and a standard deviation of the standard deviation of the errors or of the residuals. And we can see in this overlay that this overlay looks pretty good, that these residuals kind of appear to be following. Again, they're never going to be perfect, so this is a case where kind of getting a feel for how far of a deviation is too far. In this case, though, we know that the underlying distribution is normal, so this is good. This is as good as it gets. This is a normal data set, an underlying normal data set. So this graph is about as good as we get, so it looks pretty good. All right, now for the QQ plot, we're going to be using the QQ norm command to create a plot of the errors, or the residuals, excuse me. But I'm going to use the scale command. The scale command just normalizes the errors, and it makes the QQ plot on a standard framework. You don't have to do this. And in fact, the QQ plot will look just fine if you just use the QQ norm, if you don't do this. However, the line that we add can look a little bit funky if we don't. You can use QQ line to get a good scaled line. I have some issues with that. I tend to just scale the residuals and then use AB line 0, 1 to add a line that goes through 0, 0, the 0 on the y-axis, and then has a slope of 1, and my points should fall roughly along that. Now again, in our QQ plot, we mentioned our points should follow along this diagonal line, and in fact these points do follow very closely along a diagonal line. You're seeing some variation here, but that is absolutely fine. Again, we know, because we created this data set, that these errors are normally distributed. So any variation you're seeing here is the type of random variation you should expect to see if your underlying data is normally distributed. What we would look for here is patterns where the data swing down, or maybe it makes a little S shape, or it makes a little cubic shape. So those are the kinds of patterns that we would look at. However, this can be tough to tell if it's good or not. So I created a function, and actually I did attach this in the code that's available on Blackboard. You just run the source command and it downloads the function check norm from GitHub onto your computer. So you can use this check norm and scale E. Now what this does is it generates a whole bunch of random normal data sets and does QQ plots of them, and then it drops your data into that data set. And if you can pick out your data from these 9 plots, then you know that maybe your data isn't particularly normal. So I'm trying to look for weird patterns in these to see if my data is the one with the weird pattern. So I'm looking for weird patterns. Well, this one's got kind of a weird pattern, so maybe this is the one that's my data. It looks a little bit different than all the rest of them. So I'm going to pick this one and see if that's it. Now when I'm ready, when I think I've got my data, I hit enter, and then my data is going to be highlighted in red. So I hit enter, and oh no, that's not my data. This one was my data set. Oh, that's weird. So among 9 normal plots, I couldn't pick out which one was my data set from the rest of them. And you can run this command multiple times, but if in multiple tries you can't pick out your data set, then that might be a good indication that your data set is just fine with regards to normality. So looking at, I just ran it again, looking at these, well, these top 2 plots look like they could be maybe one of these 2 could be mine. They can have some weird stuff going on in the bottom tails. But if I hit enter, neither of these plots are my data. This bottom middle plot was my data. So again, what that's indicating is that patterns like this are expected under a normal distribution, just by random chance, or at least under a normal distribution with the sample size that I have. So this check norm tool can be very handy, especially while you're getting the hang of it. You would never put this in a homework assignment. So what you would do is you would run this on your own. You would see if you can identify. This is going to be really helpful in figuring out when you're looking at the normal QQ plot of your data. Is this normally distributed or not? Like, does this QQ plot look good? Does it look bad? Is this tail too weird? You could use check norm to indicate, well, is this, you could compare it to a whole bunch of other normal distributions to see if your data were too weird or not. And if you run check norm a few times and you can't pick out your data after a couple tries, well then what you would say is that there's no real difference between my data and the rest of the normal, so this QQ plot looks fine. Now what you would report though is not all of those different trials you did. You would just report this QQ plot and say this QQ plot doesn't look like it has any issues with normality. Now if you ran that and you could pick out your plot every single time, then you may show this QQ plot and say this QQ plot does indicate issues with normality. But either way, what you're going to end up reporting on an assignment or in a report is the QQ plot for your data, not what's provided in check norm. Check norm is just a tool that you can use to get a feel for, is this normal or not? Is this good enough or not? Okay, so for homogeneity of variance, we're going to look at that same residual plot that we looked at earlier. And again, we're looking for the spread of the data. Does the spread get narrower or wider? And we're looking for obvious patterns. So here, I don't really see any obvious patterns. This looks like it, well, I guess it is about the same width as the rest of them. So there doesn't really seem to be any obvious patterns of spread going on here. And typically we do have this little nice dotted line down the middle. Okay, so all of these were good, and all of these were done to demonstrate what good versions of a scatter plot, what good quote-unquote versions of a QQ plot, of a histogram, what good quote-unquote versions of a residual plot of the residuals would look like. All of these are quote-unquote good plots because they were generated with data that has homogeneous variance, homoscedasticity. They were generated with data that had normally distributed errors, with data that are linear and independent. So all of these would be good examples. Now let's dive though into the bad examples. So what I'm going to do, I'm not going to go up and remind myself what each of these things are. What I'm going to do is I'm just going to do my plots and see if I can figure out what was the problem. I remember that I had y2, y3, y4, y5, but honestly, I can't remember which one was which in terms of which one had which problem. So I'm just going to use my plots to try to distinguish which of these y values had which problem. And I know that each of these had one specific problem that was incorporated with it. Now, as opposed to running all of the plots above, I'm going to switch. What I'm going to do is I'm going to, instead of going one by one, linear, independence, normality, equal variance, going through those line assumptions, I'm just going to run the plots and then determine, taking all of the plots together, does there look like there are any issues? So recall in one of the later slides in our lecture slides, we had each of the plots and then we talked about what all of the violations we could be looking at in those plots are. So this I'm going to run for y2. I'm going to create the model of the residuals and the predicted values, and then I'm going to run the scatter plot. Okay, right away, scatter plot. This does not look linear, right? So I've got the line fit. Clearly this looks like maybe a quadratic thing is going on here. And I remember that I did have a quadratic example up above. So I think this one's probably going to be the nonlinear one, but let's keep going with the residual plot. So recall that we said the residual plot also indicates violations of linearity, and I kind of awkwardly tried to describe this on the slides, but in the residual plot we can clearly see that this is not linear. Now it's not that the homogeneous variance has an issue, because again the spread of these is roughly consistent throughout. It's that the general pattern of the middle is not horizontal, and what we said is on a residual plot the pattern of the middle of these dots should be horizontal, and clearly the pattern of the middle of these dots is not horizontal in this case. So definitely an issue with linearity, not necessarily one with homogeneous variance though, because again the spread of the points among themselves doesn't seem to change all that much throughout. Checking normality, I don't know. This is one where I might use that check norm function to see. So check norm, and I'm going to run it on scale E2 to see, because I can't quite tell. So I'm going to guess this one's mine. That's the one that looks the weirdest among all these. Oh no, it's this one. Okay, so if I run it again, can I tell? No, I don't really think any of these look particularly different than one another. Maybe this one looks different, so that bottom middle one. Oh yeah, okay, that bottom one, middle one's my data, so I'll try it one more time. Any of these look different? Any of these look different? Well, this one's kind of got that weird bump up. This one's kind of got a weird bump down. This one, the front looks kind of funky. Huh. I might go with this one, the one that has a weird bump up. Oh, but it's the one that's got the weird bump down. Okay, all this to say, my data don't look particularly different than the rest of these. there is a weird little bumpy thing going on here, but again, especially after looking at the first one, where the first one looked, the one that I picked looked way different. This doesn't seem to be particularly different than the rest of these graphs, which all have little weird things going on with each one of them. So I'm going to say that this QQ plot looks fine. It is roughly centered around this line. It does have this little downward bump, but again, as we saw with a whole bunch of other normal plots, they all have little weird bumps too, so it's not something that's too extreme to be concerned about. So after I look through these plots, then I can mentally think through each of my assumptions, and I can think through what is the best way to demonstrate that this assumption was met or not met. So linearity, this is definitely not met. So if I go back to this scatter plot, I can clearly see that this linearity assumption was way not met. And the scatter plot probably is the best visual demonstration for that. I guess I could do the residual plot too. Either one of these would be pretty good at demonstrating that linearity is not met. Independence, data were randomly generated, so we don't have to worry about independence. Again, this isn't really a plot thing. This is more a methodology thing. So we would look at the method and say, okay, yeah, the data came from different sources that aren't related in ways that the model isn't accounting for, so independence isn't an issue. Normality looks okay. It doesn't look great, but it doesn't look like it has any major issues. I did kind of have to check because it did have a weird little thing going on, but that weird little thing doesn't seem to be too weird to take it outside the realm of possibility for the normal curves. I guess if I wanted to, I could do a statistical check on this one too. But actually, if we think about it, we know from above that this used a normal distribution to demonstrate the residuals. So actually, we do know that these residuals are normally distributed. In real life, though, we wouldn't. We wouldn't know that a normal distribution was used to demonstrate this. However, it is good to know that this kind of a lump is absolutely possible with a normal distribution, because in this case we used a normal distribution and we got this kind of a lump just randomly, so that's okay. Now with the equality of variance, this one's from the residual plot. It's kind of tough to tell because of the curve, right? It's kind of tough to tell how spread are these data points. Are they equally spread across all of them? But looking at the spread for each of the x values, it does look like that this seems pretty evenly wide across all of these different predicted y values. So I'm not too worried about the equality of variance in this particular case. So linearity is the big one that was violated, and if I wanted to present a good illustration of why this is violated, I would probably present the scatter plot. All right, let's look at y3. So I'm going to run the model, fit the residuals, and fit my predicted values. Now, if you're typing along, if you just took all of this and copied and pasted down below and then did a find and replace for the number 2 to make it the number 3, I will freely admit that's what I did when I was making this sheet for us to walk through, so that would absolutely work. So we have the plot of the scatter plot. Now this looks linear. I don't actually have any problems with this linearity, no outliers, so this looks fine. Residual plot. This looks great too, so I don't have any problems with homogeneity variance, no linearity issues, no outlier issues. So this one looks, here we go. So in this case, this is our lazy S a little bit. We see it kind of ducks down, ducks up, and then comes back. Actually, the line almost hides this. But yeah, this looks hesitating to me. Now in the last one, notice it kind of ducked down and then it kind of slowly came back up. So we just had one lump, but this actually has two lumps. It has a bottom lump and a top lump that make it look like this almost lazy S shape. Now we could run this check norm command a couple times just to see. So check norm. So yeah, I'm going to pick this one. This one definitely seems to have a bit of a curve. If that's tough to see, you can also zoom in on this. So you can see in this, all of these tend to have that diagonal shape, except for this one, which kind of tucks down and then jumps up. So I'm betting the top left one. We'll see. Yeah, top left. Let's try it again, just to make sure. Now looks like top left again. Yep, top left again. One more time for luck. So looking through these plots, and again I can zoom in to see these a little bit better. Again, most of these follow this diagonal. They've got a bump here or a bump there. This one's got a little weird something going on. This guy's got a little something in the corner, but this one definitely has 2 lumps. It's got this tuck under, and then it's got the loop over. So I'm going to guess the middle plot in this one. And you see that that's highlighted. So this one clearly does have an issue with normality. It doesn't appear to be a huge issue because it really doesn't. I mean, it is pretty close to that line. And when we graph this, it does follow pretty close to the line. But what you're seeing in the tails is that these tails tend to shoot out on the corners. That is, the tails tend to drift off left really fast and drift off right really fast on the top corners. And that's what is making me pretty nervous about this particular QQ plot. So given the fact that the scatter plot looked great, the residual plot looked great, and the QQ plot's kind of questionable, I'm going to say that this one is the one where we did non-normal data. So again, linear, independence, and equal variance looked fine. Normality has some deviations, and the best way to demonstrate this would be to provide this QQ plot and describe in text how it does seem to have some drifting at the top and the bottom, and it's got these kind of 2 lumps, a lump down and a lump up, indicating that the QQ plot isn't normal. It's not fitting that diagonal. All right, Y4. So running through this, I fit the model, the errors, and the predicted values. Okay. Well, so I thought this one may be a linearity issue, but actually the line kind of does seem to fit along the middle of these. But clearly these data are much more clustered closer together than they are further apart. Let's look at the residual plot and see if that holds. Yes, very clearly we've got very close values on one side, and then as the predicted value decreases, they get much wider apart. So this one's going to be our homogeneity of variance issue. But we did have one that was homogeneity of variance and linearity. I don't see it though. I think this one actually has linearity because again, the middle, these are way wider, but the middle does seem to fall on this line. So this does appear to be linear. It just seems like the variance gets bigger and bigger as we go on. Let's check normality quickly though. Yeah, again, we've been looking at lots of normal plots as of now. So now we're getting the hang of the fact that these lumps, which may scare off first-time students, well, we've seen these several times in some of the different normal plots. We could do the check norm to see if we could pick this out. But yeah, this is, this doesn't seem to be too different than the other normal distributions that we would see. So given these plots, linearity, it's tough to tell with linearity, but I think it looks fine. Independence, again, from the method, data are randomly distributed, so no issues there. And normality looks fine too. It really looks like homogeneity of variance is threatened. And probably the best way to demonstrate this is this residual plot where we've got all the data so close together and then it gets more spread out on the left-hand side. All right, the last one. Okay, here we go. So this one, actually the line kind of is a bit distracting here. So in this one, I see that the data are closer together and then they get wider apart, but I also see that the line looks like it tucks under and then lifts up. So this is the one I'm going to bet that has both an issue with homogeneity of variance and an issue with linearity. Because again, if we fit a line, this doesn't really seem to work. The line doesn't fit these points at the beginning. It kind of fits them at the end, but it definitely seems like this is a U shape with points that are clustered close together on the left side and then wider variability on the right. So let's look at the residual plot. Yeah, we see the linearity issue on the residual plot. Again, the middle of these data points should be flat. The middle is not flat. It kind of has this bend in it, indicating that this could be a quadratic relationship. And then we're also seeing closer clusters on the left-hand side than we are on the right-hand side, indicating an issue with homogeneity of variance. QQ plot, this actually looks fine. We do have a bit of a rise and a bit of a fall, but it sticks pretty darn close to that line. I am honestly a bit worried about this tail, but it's actually not too bad because everything sticks really, really close to that line. And we're only seeing drifts on the tail on kind of one end, not on both ends, which is what we'd expect if we're getting that quadratic shape. So this QQ plot looks fine. We could throw it in that check norm function if we wanted some help in interpreting that. All right, so given these plots, looking at the line assumption, again, independence, randomly generated data, we're fine. Normality looks good to me. I think normality looks good here. Linearity, though, yeah, definitely not linearity, and homogeneity variance definitely look like they have issues. So I would call out linearity and homogeneity variance. You could use either the scatter plot or the residual plot. I think both of these did a decent job of showing the linearity and homogeneity variance issue. But honestly, I think I prefer the residual plot on this one because it does really demonstrate how the middle moves. So it demonstrates the violation of linearity. And it also does a really good job of demonstrating how the points get more and more spread the higher and higher the predicted y values go. All right. Well, let's look over the statistical tests, and then we will be done with our regression diagnostics lecture. So again, important note, significance here means that there's a violation. So if we have a statistical significance, that means that there's a violation. So there wasn't really anything for linearity, so we kind of skip linearity. For independence, we have the DW test. Recall that none of these issues should have, or none of these models should have any issue with tests of independence because they were all randomly generated. So all of these tests should be not significant because there should be no issues with independence in randomly generated data. Running through this, we get the Durbin-Watson test. So for each of the models, we find that there is not enough evidence to reject the null hypothesis, which is good. We shouldn't reject the null hypotheses for any. None of these should be statistically significantly different because we know, because we generated the data, that none of these have dependency issues. All of these numbers were randomly generated. So all of them are independent. For normality, we have the Shapiro-Wilks test. So if I run the Shapiro-Wilks test, recall that we only had one case, and I'll actually clear my screen here. Shapiro-Wilks normality test. So if I run the Shapiro-Wilks normality test, actually other than the first one, so this first one, oh, it says significant, but it shouldn't be. This actually is not significant. So if I run this, not significant, but then the rest of these all are statistically significant. But if we remember, only one of these data sets was generated using non-normal data. I don't even remember which one, but only one of these data sets was generated using non-normal data. But the Shapiro-Wilks says all of these are in violations of the assumption of normality. Now that's a problem because only one of them should be in violation. I guess I have the note here in number 3. This is the only one that should be in violation of normality. Let's go up to the top and check real quick. Which one had non-normal data? Yeah, number 3. So what's really interesting here is it's not even the, this one, it doesn't even have the lowest p-value. The one E4 with no homogeneity of variance has the lowest p-value. So this isn't even the most statistically significant one, but this is the only one where the test is correct that we have violated normality, and we know that because we generated the errors from a non-normal data set. So this is important to realize with the Shapiro test, and again, why I recommend not using statistical tests or only using them in conjunction with the plot. So if you recall that plot, it kind of looked like it had a lazy S, but we weren't sure. So maybe we would run a Shapiro test to check on that. And what we would say then is Shapiro indicates a statistically significant threat to normality for the data set that we're working on. This would be the outcome 3. Combined with our QQ plot that also seems to show a violation, we conclude that there is a violation of this assumption. So what we would do is we look at the plot. If it looks like it may be in violation, we run a test. This test says, yes, it's statistically significant. That statistically significantly is a violation of the assumption. And so we conclude that the assumption is violated. Again, though the fact that this is statistically significant doesn't really mean anything, because for almost all of our data sets it was statistically significant, which indicates that this test isn't really to be relied upon. Now, the Shapiro-Wilks is a good test. The problem is that Shapiro-Wilks is sensitive to things like, well, if the data aren't homogeneous, then the Shapiro-Wilks comes out as statistically significant, and if the data aren't linear, apparently the Shapiro-Wilks comes out as statistically significant. So it's just sensitive to lots and lots of different things, and this is even at a reasonably small sample size of 100. If we had larger sample sizes, the Shapiro-Wilks would probably be performing even worse. So this is why we don't use the statistical tests, is again, they show significance for a whole ton of stuff that they shouldn't show significance for. But if we want to use them in conjunction with a plot, if we look at a plot, it looks like it may be showing a violation, then we can run a test to help us make a decision about that. All right, for our last test, we have the test of homoscedasticity. We'll run the Broche-Pagan. Now, this one, I'll clear the screen with Control-L real quick. So this is from the package LM test, and I'm going to run all these. What you'll see is very similarly, we have a Broche-Pagan test that indicates a statistically significant difference, even though there shouldn't be one. So these first two, the Broche-Pagan test correctly concludes that there isn't an issue with homogeneity of variance, because these two data sets didn't have an issue with homogeneity of variance. The variance was constant in these. But for the third one, where we had the violation of normality, the Broche-Pagan test tells us that there was a statistically significant violation of homogeneity of variance, even though we know that there wasn't one. So what we could say here is something like the Broche-Pagan indicated a statistically significant threat to the homoscedasticity. Scatter plots and residual plots don't indicate a meaningful threat. Thus, we conclude that there's no threat. Now, in the method that I tend to use, which is we look at the plot and then we supplement with the statistic, looking at the plot for Model 3, we didn't see any issues. In fact, the homogeneity of variance looked almost perfect. I want to show you this because, again, our test is indicating a statistically significant violation of homogeneity of variance. But let's look at this plot one more time. If we look at this residual plot, how can you say that this is a violation of homogeneity of variance? It's almost perfectly homogeneous in terms of the variance. So one of the things I want to call out here is that these statistical tests sometimes overlap. That is, sometimes the homogeneity of variance tests will show statistical significance when there is a lack of normality, and vice versa. Sometimes the lack of the normality tests will show significance when there's a lack of homogeneity of variance. So these things do tend to be related. That said, this is why we tend to look at graphics, not as much the statistical tests. Now, for these last two, there was a violation of homogeneity variance, and the test correctly indicates that these two did not meet the assumption, or there is evidence that they did not meet the assumption of homogeneity of variance or homoscedasticity. So for these last two, these are statistically significant, and they should be statistically significant. For the first two, they weren't significant, and they should not have been. So these first two are correct, the last two are correct. The only one that the Broche-Pagan got wrong is the middle one, and it was still pretty close to the 0.05 cutoff. It was pretty close. But it did declare that this was statistically significantly in violation of homoscedasticity, when in fact the data really wasn't. So in these last two cases, we would indicate that in conjunction with the plots, and the plots definitely showed violations for these last two models, if you remember those plots, very, very clear violations of homogeneity of variance. So we would take these statistics potentially into account with the plots, or frankly, we would just use the plots. When I'm doing analyses, I do tend to focus on plots. There are occasions when I will run the statistical test, but typically, as a rule, I tend to look at the plots and really focus my attentions and my decisions based purely on the plots. In this video, We've talked about how to run regression diagnostics for simple linear regression using R, discussing what good pictures look like, what good plots for residual plots, scatter plots, QQ plots, etc. look like in R, and we've also discussed the statistical tests, or a few statistical tests that can be implemented to check these assumptions.